Okay, looking good. Okay, good morning, everyone. Thank you for having me here. So today I'm going to talk about our recent research effort in trying to clean up the tandem mass spectrometry data for better metabolite annotation and unknown discovery. So I'm in the Department of Chemistry at the University of British Columbia. So my lab, I'm an analytical chemist, and my lab mainly focuses on the synergistic development of analytical chemistry and bioinformatics. The goal is to make a fundamental improvement of mass spectrometry-based metabolomics in terms of how can we better detect, quantify, and characterize small molecules using mass spec. So, mass spec really does not. The only thing mass spec do is to measure the mass to charge ratio. And sometimes when we want to get the chemical identities, we really need to use this tandem mass spectrometry approach to collect the fragment ion and compare against database or do some de novo annotation. So the quality of MS spectra is critical to the exploration of the chemical world. However, there's a problem of chimeric MS. This happens when we have this target compound sometimes co-elute or elutes very closely with another interfering compound of similar M over Z values. And when we are triggering the MS event, we usually use a quadruple mass filter to purify and select the target ion. The problem here is that if the inference compound has similar M over Z value as the target compound, then they will all get into this collision cell. And when the fragment process happens, both the precursor, target precursor, and also interfering compound will be fragmented into pieces. Therefore, in the MS spectra that you collected for the target compound, you might have some interfering MS, or we call the contaminant MS, or called chimeric MS, that will interfere with the purity or quality of the spectra. And for example, it's very easy to understand. For example, we have two compounds, DUMP and the glutathione. They have very similar M over Z values. They cannot be distinguished by the mass filter, the quadruple mass filter. And when you collect experimental MS, you will see the fragment of the glutathione in the MS or DUMP, and then you will see the peaks of the DUMP in the MS of glutathione. And it's easily to understand that this contamination will reduce the spectral quality and also cause problem for spectral matching score. And what's really important, and we want to emphasize here, which you have not been previously studied, is the impact of those chimeric MS on molecular networking. Because these days people realize that there are so many unknown compounds, and the molecular networking and the spectral similarity analysis is a critical tool to address them. However, because the experimental MS spectra is contaminated, the spectral similarity score you calculate might be affected. So here's a demonstration. We can take some metabolites. We run these metabolites using this target MS approach to generate high quality MS spectra. On the other side, we have the SMELS file, so we can calculate both their spectral similarity and the structural similarity. Then we can map them into this 2D diagram where the x-axis represents structural similarity, y-axis represents a spectral similarity. And then we can repeat this process for all these pairs. We can randomly pick a pair of spectra and calculate the similarities, and eventually you will get a plot like this, a scatter plot. For some pairs, the structural similarity is a good indication of their structural similarity, while others might be not. For example, those dots located in this area and in this area. Okay, so here are these MS spectra high quality data, and we can also randomly add this noise into these spectra to generate the contaminant MS spectra or chimeric MS spectra, and we can redo this spectral similarity in the calculation, and then we will find that those pairs will show up in this red dot. So visually, you can clearly see that for those pairs with high spectral similarity, they get a reduced spectral similarity after they've been contaminated by these randomly added noise. However, for those pairs that at a low structural similarity range, their spectral similarity actually got artificially higher because of the contamination. So the explanation is that when you have this contamination, it will artificially generate more random hits. Therefore, you will get a slightly higher spectral similarity. And then we also repeat this process using the NIST-20 spectral database with the tens of thousands high-quality MSMS spectra. We also, generate these contaminated MSMS, and then we try to take a look, as you can see, once the MSMS spectra is contaminated, the similarity score will drop. And then if we take these pairs in both high similarity and low similarity regions and do this correlation analysis, we find it's actually negatively correlated. And this is all because of the chimeric MSMS. When you have pairs of high spectral similarities, the chimeric MS spectra will bring down their spectral similarity. On the other side, you have a low structural similarity, then these chimeric MSMS would boost up their spectral similarity. So in both cases, it's not what we want, and it's bad to these molecular networking analysis. And we can do another by changing those the intensity ratio between the interference and target. In this case, 1 to 10 means that the intensity of the interference is only 10% of that for the target, and then we can do 1 to 5, 1 to 1, 1 to 2. Eventually goes to 1 to 1, which means that the interference had a similar intensity as your targeted precursor. And then we can see how those spectral similarity dropped significantly. And then the change of spectral similarity really shifted to the negative side, affecting all those spectral similarity analysis. And we are not the first research lab to recognize chimeric MS spectra. And we find, to our knowledge, the first work we find back 2010, a paper published in Journal Proteome Research. People study the impact of chimeric MSMS spectra on peptide identification. And then in the metabolomics field or in the chemical analysis field, Dr. Daniel Raftery's lab in the University of Washington, they developed this Ramsey strategy, and then this is more for targeted MSMS analysis, where you can get a continuous these kind of chromatogram of both the precursor and also the fragment. From there, you try to pick which is a true fragment and which false. And more recently, Dr. Gary Patty's lab and Washington University in St. Louis developed this decoy ID strategy to simply to purify those chimeric MSMS using a spectral library-based approach. In this approach, they basically comparing their experimental MSMS spectra against those library high-quality MSMS, and they use that to deconvolute the experimental MSMS to generate the high-quality data. And our lab is more focused on data-dependent acquisition. How can we clean up those MSMS spectra? And we published 2 papers in the past few years. The first paper actually coincidentally published around the similar time as the DECO ID, but we comes from 2 completely different approach. And the second paper was published more recently. So in my following work, I'm going to introduce these research efforts. So the first one was done by my student and now the postdoc, Dr. Fiehn. So in this work, we first see, there's some contaminated MSMS in the contaminated fragment in the MSMS spectra. How should we remove them? So the idea is that we can take the same biological sample, we run the sample in the data independent acquisition mode. Then from the data independent acquisition mode, we try to find the chromatography of both the fragment ion and the precursor ion. So as you can see in the DIA analysis, if the fragment co-eludes very well with the precursor ion, then we believe that this fragment ion is more likely to be a true fragment. However, if the fragment ion shifted a little bit by the retention time, then this fragment ion is more likely to be a fragment of another precursor ion. And sometimes we might also see the fragment ion intensity does not really show a peak, but rather just fluctuate across the retention time. In this case, we believe that this fragment ion more likely comes from those contaminated in the system or from the solvent. And of course, not all the fragment ions can be found in the DIA analysis. In those cases, the peak-peak correlation will be NA or not available. Then based on this DIA analysis approach, we designed this kind of experimental workflow to train a random forest model. The idea behind is we have the DDA data generated, then we run the sample again to get the DIA data. From the DIA data, on one side we calculate all the peak-peak correlation between the precursor and the fragment ion, and also we check some others, ideal slope and sharpness. All these are, we believe, they are possible features that can be used in the model. And on the other side, we do manual inspection by manually take a look at the peak-peak correlation in the DIA analysis to tell whether it's a true fragment or more likely to be a false fragment. From there, we trained a random forest model. And furthermore, based on this model, we developed a complete bioinformatical pipeline called MS2 purifier. So this is an integrated algorithm where users all they need to do is to input the DDA data together with the DIA data. Then we will automate the process of the feature extraction, MS1, MS association, and then do the EIC extraction and the model prediction. So finally, we will be able to automatically purify the original MSMS to the purified MSMS. And we tested our model. We see a really good performance. And as a demonstration, we basically change the parameter of the isolation window width in the MSMS event from 1 Dalton to 8 Dalton. We can see how the percentage of those contaminant the true fragment ion dropped and the contaminant fragment ion increased. And we also tested both chemical standard and the mouse fecal data set. We calculate the percentage of true fragment ion and the false fragment ion, or sometimes contamination fragment ion in that paper. And we find that actually there's a certain level of contamination. And then by purifying the MSMS spectra, we see the improved match ratio in both the chemical standard and the fecal data set. So this is a work where you can run the sample again in the DIA analysis to help purify the MSMS. Then we think about, can we really simplify that approach without doing any extra analysis? This is because sometimes we might finish the data analysis, we might generate data many years ago, and we don't have the sample available, and it's not feasible to run the DIA analysis. So because of that, we come up with an idea called de novo cleaning. So the idea behind this is to directly look into the metabolomics data set and try to find certain patterns for the true fragment ion and false fragment. So the idea behind this is trying to look for the signal variation across samples. So here we can see, we have 3 samples, and we have the target, the precursor ion exists in all these 3. And because of those analytical and biological variation, the intensity of this metabolite or the intensity of the target precursor ion might be high in sample 1, but low in sample 2. You have this kind of a fluctuation. However, no matter what fluctuation you have, those true fragments should all go up and down together, right? Because they all come from the same precursor. However, those those false fragments coming from the contaminant precursor might not go the same direction because they are independent. They are really sample dependent and nothing to do with what metabolite you're talking about. Because of that, we can actually take a look. So all we need to do is to identify a driving peak in the MSMS spectra and calculate the ratios between those pairs. So for the true fragment ion, because it goes all up and down together with the driving peak, so the intensity ratio fluctuation will be relatively low. On the other side, for the contamination fragment ions, because it's independent of this driving peak, so its ratio will fluctuate a lot. Then all we need to do is capture this signal ratio fluctuation, and from there we'll be able to tell whether a fragment is a true fragment or false fragment. And this is easily done by using this relative standard, calculating the relative standard deviation of the intensity ratios. And we designed the experiment to show the possibility of achieving de novo annotation using this approach. We took a urine sample. We also prepared a pool of metabolite standards. Then we mix the urine sample and the metabolite standards in different ratios. And then from here, we mimic a real metabolomics study where the metabolites have different concentrations in different samples. And then we collect mass spec data. From there, we have the experimental mass spectra. Then we calculate the intensity ratios. On the other side, we can manually label whether a peak is a true fragment or false by comparing against the NIST 20 high-quality mass spectra database. So here's an example. We have two compounds, right? It looks very close to each other. And from there, we can manually label which are the true fragments, which are the false fragments. And then we can take a look at their intensity ratios. As you can see, these true fragments usually have a relatively low variation compared to the false fragment. This is true for both cases. And also we can view it for all these metabolites that we spec in, all these fragments we know in these samples. You can find that the distribution of the ratio RSD of the true fragment, the ratio RSD of the false fragment. So you can see it's quite different between these. And we can actually, if we use these ratio RSD values, we can achieve a 0.91 AUC already. However, we think it's important to include more features. For example, we believe that if the fragment, the true fragment, then it should appear in all these MS spectra, while if it's a false fragment, it's more likely to appear in some of the spectra, maybe not the others. And also intensity, we think that true fragment might have relatively high intensity and false fragment might relatively low intensity. Although these two features are not very strong in making the prediction, but they can still achieve independently and give some power there. So eventually, we have our training data set. We split and we do machine learning training, and then we try to build up this pipeline. In this work, we tested, we included all these three features, including the ratio intensity RSD, and also the appearance rate and the intensity value. And also we tested different machine learning models, and the performance are very similar. There's no big difference. It makes sense because this is a relatively easy machine learning study, machine learning task. So eventually we choose this XG Boost as the model to use, and we didn't really stop from the model. We also developed a pure integrated bioinformatics solution. In this case, because of de novo purification, so we add a DN MS2 purifier to distinguish from the previous work that we did using DIA approach. So the idea is simple. We want to make it as easy to use as possible by streamlining the entire data processing workflow, so that all the user need to do is raw LC-MS data to as the input, and then we'll get a purified MS spectra, and also in MSP format that can be directly used for spectral annotation and also the molecular networking analysis. Again, so first the testing is on the different isolation window width, and we know that with a larger isolation, the MS isolation window, you will have more false fragments, and then this is agreed to what we discovered in the work, and also we tested how that using the purified MS, we get a better spectral annotation. And in this work, we also check the performance in the molecular networking by connecting this known MS with the unknown MS using the spectral similarity. And after this purification, we find that we can identify or establish another 1,733 new edges, and among them we get extra 200 connection between the identified metabolites with these unknown compounds, and also there's 62 between identified compounds due to the improved spectral quality. And more impressively, we find over 1,400 these spectra unknown relationship that's been newly established after purifying the MS. So with that, it's my short presentation about these two works, and I'm happy to take your questions. Thank you.
Yeah, can you see my screen? Okay, great.
Yes.
Okay, so now today I want to share our works on a fast spectrum similarity comparison. Our title is flash entropy. We developed. So first, let's go for the MS spectrum. We know let's take this example. Let's say we have 5 precursor ions. Out of fragmentation, it will generate 2 types of product ions. And then the mass spectrometer will detect at least 5 product ions and generate the MS spectrum. And then we can identify these molecules by comparing the MS spectrum against the library. And then the first question is like how to compare the MS spectrum. And we believe like a MS spectrum is a probability distribution. And then, for example, let's go back to this example. And in this case, we can say we have like a 60% chance to get the green product ion and a 40% chance to get the pink ions, right? And then we can plot like the general entropy ideas from informatical theory and calculate the spectral entropy. And after that, we can compare the spectral similarities by entropy similarity. How to do that? Let's say we want to compare these two spectrum A and B. First, we generate a mixed spectrum. Then we calculate the spectral entropy for those three spectrums. And then we can also calculate the entropy gain between the mixed spectrum and the two previous spectrum. After that, we will have spectrum distance equals like the sum of the entropy gains. In this case, it's like which equals the S mix minus SA plus S mix minus SB. And then we can have the entropy distance. After normalize the entropy distance into 0 to 1, we will have the entropy similarity. And if we go back to like the idea of the spectrum, MS spectrum is a probability distribution, we can have another definition of the spectrum similarity. It's like a spectrum distance equals the probability distribution distance. And one of the widely used probability distribution distance is called Jensen-Shannon divergence. If you go to like a statistical book, you will find this. And interesting, like if you scale the Jensen-Shannon divergence into 0 to 1, then you will find the entropy distance is mathematically equal to the Jensen-Shannon divergence. And then basically, like entropy similarity is similar to is equals to the probability distribution distance. Okay, after that, we test the entropy similarity's performance against the dot product similarity in the LCMS, and then we find it outperforms like a dot product similarity a lot. And then we think it's good, and then so we publish these ideas, and there are many different labs. They also try the entropy similarity in other like scenario. For example, in this lab, they find the entropy. They test the entropy similarity in GCMS, and they find the entropy similarity can have like a 20% increase in identification accuracy or the cosine similarity. And this group, they test the entropy similarity in the proteomics. They find the entropy similarity. They compare like different multiple like spectrum similarity, and they find the entropy similarity always like is the best. And also this group, they compare the entropy similarity against like a dot product similarity and the square root dot product similarity, and also other like spectrum triangle and the Pearson correlation and other stuff. And then they also find the entropy similarity is always the best. So after this, I think we solved the first question. Like we think we can use the entropy similarity to compare the MS spectrum. Then let's go to the next question. It's like how many types of spectrum comparison? In traditionally, most people when people do like a spectrum MS spectrum comparison, they only compare like the spectrum within the same precursor M over Z. And then this idea works very well, and but it can only be used to identify the molecules with the same molecular structure. Let's say if your unknown molecule have exactly the same structure as the library molecule, with the identity search you can find it. However, in metabolomics field, we have many unknown molecules. They are not in the library, right? And if you use identity search, you cannot find it. Therefore, you need to go beyond the identity search. For example, in this case, you want to your unknown molecule have like a majority like the molecule group is similar to the library molecule, but it have like a 1 or 2 more functional group. So use identity search, you cannot find these types of molecule. And to solve this problem, like many people have like a development methods. For example, one the use the method in the proteomics field is open search. They when with this types of spectrum combination, we not only like compare the spectrum with the same precursor MOZ, but also compare the spectrum with different precursor MOZ. And then you can find like the molecules is without like they have like different structures. And another work is like called neutral loss search, which is published, which is used in Metabolomics database. In this work, you do not you are not only consider you consider both the product ion and the precursor ions MOZ, and then you calculate the neutral loss. This method is similar like the open search. You compare the per fragment ions MOZ, but it compare the neutral loss molecular mass. And this method is used in Metabolomics database. And also another type of search is called hybrid search. This method is like a combination of the open search and the neutral loss search. It compares like both fragment ions and neutral loss fragment matches. And this type of match is also called like a modified cosine in GMPS network. And this type of search is used in like a NIST-MS search and the GMPS. So I think in the metabolomics field, like a lot of people like this type of search. And then if we go back to see like those 4 different types of spectrum comparison. For the identity search, because you only need to compare the MS spectrum have the same precursor mass. Therefore, you have very small like searching space. However, for the open search, neutral loss search, and the hybrid search, because you need to compare all of your spectrum against like all the spectrum in the library, then you have very large, much larger searching space. Let's say in the MONA database, there is about 2 million spectrum. And if you go to like the public repository, there is around like 1 billion spectrum there. So if you want to search like compare your spectrum against whatever MONA library, you need to search 2 million library, 2 million spectrum. And if you want to search your spectrum against the whole public repository, like the MSST, you need to search your spectrum against 1 billion spectrum. And therefore, if you use the occurrence method, you will find the problem. Like searching like the whole library takes too much time. Therefore, we need a better method. So here comes the third question, like how to increase the spectrum comparison speed. And we think here we use like two ways to increase the speed. First step we do is like we simplify the entropy similarity calculation formula. As I showed you before, entropy similarity is very good. It's better than the dot product similarity. So we want to use the entropy similarity to compare the spectrum comparison. However, if you use entropy similarity if you want to calculate entropy similarity, you need to merge the 2 spectrum first. And this takes a lot of time. Therefore, we develop we do some mathematically calculations on the entropy similarity formula. And then we developed a new formula to calculate entropy similarity. We found the entropy similarity can be calculated with this formula. This formula looks like a slightly complicated. I just show you an example. For example, if we want to compare these 2 spectra, the upper spectrum have 2 ions with intensity 0.4 and 0.1. The bottom spectrum have 2 ions with intensity 0.3 and 0.2. And only the 0.4 and 0.2 ions match have the same MOZ. Therefore, the entropy similarity only depends on these matched ion pairs. To calculate the entropy similarity, first you take the 0.4 and 0.2, you add them together. Then you get 0.6. And then you calculate the F0.6 minus F0.4 minus F0.2. Here the Fx equals x times log 2x. And then you put this 0.6, 0.4, 0.2 into the x times log 2x. You can calculate the values, and then you got an entropy similarity. And I believe with this formula to calculate entropy similarity, it's really easy to calculate. And this formula avoid like the spectrum merge, and it can save a lot of time. And it's really easy to calculate. And it have like the same result. It always gives you the same result as the previous entropy similarity formula. And the second things we do is like we develop a new spectrum comparison algorithm. If we search your one spectrum against the whole spectrum library, we will find more than 90% of the spectrum they do not have any overlapped peaks. And basically their spectrum similarity will be 0. If we spend a lot of time to calculate those like zero similarity spectrums, we will waste a lot of time. So we want to avoid like this waste, and we only want to calculate entropies like for the spectrums have like overlapped matched ions. With this idea, we developed a flash entropy search algorithm. Let's say this is like this is one spectrum library. You write like every fragment ions in the all of the library spectrum, like line by line. Every line is one fragment ion. For example, like this one means it comes to the spectrum ID 5 with M/Z 121 and the intensity 0.3. And here I want to say like before you build a library, you want to normalize all of your fragment ions into the sign equals 0.5. And after we make get list tables, first step we want to index the spectrum library, which is you can make a list step by sort by the ions M/Z. You just do the sort, then that's all. And then if you have an unknown spectrum or experimental spectrum, you can search the peaks in the spectrum one by one and find the matching peak pairs. For example, in this case, we find this peaks in the QLE spectrum match to this peak in the shorted library spectrum. After that, we put these intensities from the matching ion pairs into the formula I showed you before. And then we can calculate the similarity distributions. And then after that, let's say in this case is 0.69. After that, we will put this 0.69, use this number to update the similarity table. First, before we do the flash entropy search, we suppose like every spectrum in the library have like a 0 entropy similarities against like your unknown spectrum. And then let's say here you find a match. You find the number 5 library spectrum have a peak matched with the QLE spectrum. And then the spectrum similarity contribution is 0.69. And then you will add these numbers to the similarity table, get the 0.69. And if you have multiple like fragment ions, you can do this again and again, and you will get like after you search all of the peaks in the QLE spectrum, you will get the final spectrum similarity table. And this will be the final spectrum similarity. And with this method, you can calculate like an open search and the neutral loss search. And for the hybrid search, you need to consider as I showed you before, you need to consider both the fragment ions and the neutral loss ion. And so in this case, you just do the index and find the matching pairs by the fragment ions M/Z first. Then you do the same steps, but using the neutral loss mass. And after that, you will find many like matching ions. Then you merge these matched ions, and remove the duplicates. And then you calculate the similarity contribution with the same ideas, and update the similarity table. And after that, you can get the hybrid search similarity. Okay, so after this, we want to know like the performance of this like flash entropy search algorithm. So first, we think our method is fast, which is like more than 10,000 times faster than the traditional method. or you can search like 1 million spectra in 1 millisecond. To test the speed of our method, you can see that first we randomly select about 200 spectrons from the MONA database, and then we random sample the MONA database into generator the library, which different size of library, for example 100, 1000, 10,000, 100,000, and 1 million library, and then we search this 200 spectrons against this different size of library spectrum, and we find when we search 1 million library, it needs around less than 1 millisecond to perform open search against those 1 million library. So we think our method is fast. You can see we also compare 3 different algorithms. We can see our method is much faster than the other method. And I think the second advantage of our method is our method is powerful. Our method can calculate all of the identity search, open search, neutral law search, and hybrid search. And here we also test we use we randomly select 200 spectrons and search against those 1 million library. And in those 4 different type of search, we can see it works it always have a very good performance in those different type of search. And here I also want to mention there are many fast library search methods. Let's say here I showed in Blink, and also there I also have some method will be published. And many of those methods they cannot do hybrid search, but our method can do it. And because hybrid search is much favorited by the metabolomics field, so I think our method will be very good. And then I also want to mention our method is accurate. It has 0 errors of the calculations. In this case, we compared our method's result against the traditional method. And here I also take the Blink method as a comparison. And the Blink method, they also can do the spectrum comparison very fast. However, we find Blink, this Blink method, they can have many they will make some mistakes. And in the worst case, it will make around 0.4. The similar difference between the result and the real result is have 0.4 difference. This is huge. However, with our method, the result is really accurate. It will have 0 difference. And I also want to mention our method is very flexible. If you do some modifications, it can also work to other spectral similarity. For example, for some case, all I told you the entropy similarity works better than the dot product similarity. However, for some reason you still want to calculate the dot product similarity, you can also use our algorithm. Here I just showed use our algorithm to calculate the dot product similarity. You can see it also have very good performance. You can search 1 million spectrum in less than 1 millisecond. And then I also want to mention our algorithm have excellent multiple thread performance. Let's say if you have multiple spectrum, right? In one experiment, usually you may have 10,000 spectrum. Then if you want to search all of the 10,000 spectrum, then you can use your computer usually have many cores, right? And then you can use multiple thread to increase the searching speed. For example, here I show you an example. I searched about 100,000 spectrum against the 1 million spectrum library. And you can see if you use one thread, it needs around 100 seconds. However, if you use 8 threads, the searching time is less than 20 seconds. So this is super fast. And it will also with minimal memory usage increase. And then I also want to show you if you use our method to search the big data. As I told you, in the public repository, there is around 1 billion spectrum. And then, but you do not have a very good computer. Your computer maybe have very low memory. And you can use our method. Our method have need a very low memory. And meanwhile, I know a lot of people you have like a GPU, and our method can also be boosted by the GPU. For example, here we download all of the 1 billion spectrum from the public repository. Then we search it in like a computer with like with a memory only like a 64 gigabyte. And the whole data, if you consider all of the open search and the neutral loss search and the hybrid search, it have like it needs a size like nearly 1 terabyte. But we can do the search with like computer only have 64 gigabyte. And then you can see here we test like the different search times. And you can see if you do the open search against this like nearly 1 billion spectrum, you will get like your job done in less than 2 seconds. If you want to do a hybrid search, you can only need to spend like, let's say around 5 seconds, and then you can finish all of the spectrum search. So, or you can do whatever like a search against a 1 billion spectrum in like a few seconds with our method. And then this is, I think, is like the advantage of our method. Okay, and then here I also wanted to show you like the tools to calculate entropy similarity. And if you write a program, you can use the MS entropy package. You can download it here, and it now supports Python, R, C, and JavaScript. And but I only unfortunately for the flash entropy search algorithm, you can only use the Python package. And but if you only want to calculate like a spectral similarity, and you can use RC and JavaScript. You can download the package here, or from the Python PyPy or C RAMs. And if you do not want to program, I also made a GUI called entropy search. You can download it from here. There's a barcode here. This software, it can perform identity search, open search, neutral loss, and hybrid search. And you can use this GUI to search your spectrum file against another spectrum file or spectrum library. It works in Windows, Linux, and Mac. And at the end of our talk, I want to thank you for your time, and also want to thank you my supervisor, Professor Oliver Fiehn, and also the people in the Fiehn labs. And thank you, and I'm happy to take questions.